Let's see. Okay, good morning, everyone. Let's start the first session of today in this morning. And the first speaker in the first session in this morning is Professor Laurent Perron from today's platform from University to us. And his title is Local Estimate of Solutions of the Chip-wise Equation. Please.
Thank you very much. So it's a pleasure and a honor to be there. And of course, to take part in the commemoration of the memory of Marek. This is it works up. No. Okay. How does it work? Center. No, but it's to shift page. This is no, this one. Why the back? Okay. So this doesn't work. Good question. This is a good question.
Because this guy is changed.
So, I was not totally under the phone. That was a problem. Okay. Okay, thank you. And since I'm here, I would love to recall an old friend of us, was former professor in University of Number, is Ireneo Peral, that we knew for more than 40 years and passed away 3 years ago. But a very good friend, a very good mathematician. Okay, so this is a joint work with Marie-Françoise Bigeaud-Perron, and it was just here in calculus of variation. So we are interested in analyzing the properties, in particular the local properties of this, the solution of function u, which satisfy L. PQM of u is this equation minus Laplacian of u minus up plus m grad uq is 0. And in the range that p is bigger than 1, q is bigger than 1, and n is positive. Okay, this is called Shippo-Weissler equation. They introduced this equation in the framework of studying particulars. They were very much interested in the parabolic associated parabolic equation. And after that, there were much work by Jim Serene and Zhu and collaborators also for studying properties, global properties of this equation. Okay. The domain we consider is either a puncture ball or the complement of a ball. What is the interest of this operator LMPQ? We have two reaction terms, which are grad and UP, and they go in opposite direction, and they are of a different nature. So for this, we have three fundamental exponents, which is alpha, the 2 over p minus 1, beta is 2 minus q over q minus 1, and gamma is q over p minus q. I'm going to explain why. And there is another coefficient which is important, is this sigma is p plus 1q minus 2p. Okay. So what happened? When the case where q is 2p over p plus 1, that means when sigma is 0, then this equation, LMPQ is 0, is invariant under the scaling transformation. T of u is L to the alpha. Remember, alpha is 2 over p minus 1, u of Lx. In that case, when q is 2 over p, when q is 2p over p plus 1, the three coefficients, alpha, beta, and gamma coincide. Now, the critical value of q, this critical value of q plays a very important role in the analysis of the solution. When q is less than 2p over p plus 1, in the study of a large solution, for example, of singular solution, essentially the behavior is given by the solution of the Lane-Hemden equation. It is minus delta u minus u to the p is 0. So this is a case. Now, by contrary, when q is between 2p over p plus 1 and p, then the diffusion becomes neglectable, and the behavior of singular solution is modeled by the A-canal equation, up minus m grad uq is 0. Furthermore, when you go to, instead of looking for singularity, you look at behavior at infinity, you exchange the role of the range of coefficients. Okay. Now, a third equation will play a role is, I call it the Riccati equation. It's minus Laplacian of u plus m grad uq is 0. And of course, for this value, the value of, for this equation, the value of q with respect to 2 is important. And the key exponent here, okay, the key exponent here is beta. The key exponent here is gamma, and the key exponent here is alpha. So we have the role of those three exponents. Now we look at a priori estimate. If we look at a priori estimate, we have the following form. If n is bigger or equal to 2, p is less than n plus 2 over n minus 2, and u is a positive solution of my equation, L MPQ is 0 in omega. We have the following. If q is strictly less than 2p over p plus 1, then for any m, we can find a constant that u of x plus grad u to the q to the power 2 over p plus 1 is bounded by c, 1 plus the distance to the boundary of omega to the minus alpha. So 1 is important, of course, here. And that means essentially that u is bounded by x to the minus alpha, and q is, and grad u is bounded by x to the minus alpha minus 1. Okay, this is the meaning of you right. Now, if q is equal to 2p over p plus 1, then in that case, there exists two positive constants, which are the c, dependent on n and p, and m0. such that if m is smaller than m0, in absolute value, it does not depend on the sign, then you have the same u of x plus gradient to the x to the 2 over p plus 1 is bounded by c times the distance from x to d omega to the minus alpha. As a consequence, there exists no ground state in Rn because you take omega to be br and you let r go to infinity. Now, a little about the history of those estimates. The statement 1 is due to Polaczek, Whitner, and Souple via the call it doubling method. And the statement 2 is due to Bideveron, Garcia-Huidobro, and myself, and using in 2020. And which we use for that technique that we developed for this equation here. And those techniques are extremely heavy. And they use the Bernstein technique, also the technique which are developed by the integral technique as in paper of Gillas and Sprague. And so for this equation and for the case of equation LNPQ, it is even a little more complicated to make new change of volume. Okay. Now, to start now with a new result, I'm going to speak a little about next result, which is a very important one if we study a radial solution. So if, okay, the result will be for super solution, but of course for radial solution it's the key important. I take U to be a continuous function, which is either in the complement of BR0 or in BR0 minus 0. And I denote by mu of r the infimum of u of x on the sphere x equal r. And the next result we present improves the previous result of Alarcon, Garcia-Melian, and Guas. And for that, we use a bootstrap technical lemma of Moser type, which which is has been already used in many other, in a few other papers of Marie-Françoise, and which is a very powerful thing. So what is the result actually? The result is the following. I assume that n is bigger than 1, pq are bigger than 1, and m is positive. First, I look at problem in exterior domain. If U is a C2 positive super solution in the complement of the ball BR0, then you have the following case. If 2Q is between 2P over P plus 1 and P. So there exists a constant C which depends on a lot of things, including U, such that the average of U on x equal r is bounded by c r to the minus alpha. Alpha is, I recall, 2 over p minus 1. This is for x bigger than equal to 0. Now, when q is between 1 and 2p over p plus 1, then the estimate is mu of r is bounded by c r to the minus gamma. So here it is Lehmann, here it is Eikonal. Yes. And now the last case, of course, we can also treat which when q is bigger than p and u is bounded, which is a very important case, then we have this same estimate as here. Okay. Now, if we look for solution in a singular solution, that may be solution in a ball. So it is essentially reversed. That means that I take U to be a positive C2 super solution in BR0 minus 0. Then for Q is between 2 over P plus 1, 2P over P plus 1 and Q. So we have the estimate of the Eikonal type close to 0. Okay, mu of R is bounded by C R to the minus gamma. Contrary, if Q is between 1 and 2P over P plus 1, then we have an estimate of Lehmann type that mu of R is bounded by CR to the minus alpha. Okay, now important fact is that when Q is bigger than P, in the next, remember that I made in theorem in 1, 3 before, I assume that U, I take for Q bigger than P, and U is bounded. Why U bounded? For this reason, if Q is bigger than P, the solution in an exterior domain may not be bounded. And the important fact is to note that, for example, this solution U of X is Xm times m to the gamma to the Q, absolute value of gamma to the Q, 1 over P minus Q, and this to the power gamma, so in that case positive, is a subsolution. So that means the Econal equation became dominant, clearly dominant, and at that case, in the exterior domains are not bounded. Now we want to explicit a little what is in this theorem in the case where Q is bigger than P, and we want to go a little further to this assumption where we use the fact that mu is bounded in order to have an estimate. Okay, so what happened? Now I assume that Q is bigger than P, bigger or equal to P. I take a positive super solution in the complement of the ball B R0. Then in that case, for rho larger than R0, there exists a specific constant here. Okay, so that we have the following: either U of X is bounded by Xm times X to the Q over P minus Q. Okay, or in the case where Q equal P is C1 m to the 1 minus 1 over m times X. So that means solution are below at infinity. Or P is bigger than n over n minus 2, and the average mu of X is bounded by some constant times X should be an absolute value, not a bracket, an absolute value X to the minus alpha, and U of X is bounded by the fundamental solution, bounded from below. This is bounded from above. This is average, and this is bounded from below by the solution of just the solution of the Laplace equation. X will be 2 or minus. Okay.
So what the mean of bracket?
No, it should be absolute value. Sorry, I explained. It should be the norm of X. But it is so small difference. This is not a new thing. And what is the technique for that? It's a complicated combination of Bernstein, Keller-Wasserman, and Moser-Iterowski scheme. Okay. This is it's a rather technical method. I just say a little word after that. And for example, with this type of technique, we prove fundamental estimate of singularities of asymptotics always in the case where Q is bigger than P. And I'm going to say a little of word on that. I take Q is bigger than P, always bigger than 1. And M is positive. I assume that U is a non-negative solution in some domain G of R. Okay? Now, if G is a puncture ball, BR0 minus 0, then you can find a constant C, which depends unfortunately also on U, but far from the origin, such that the grad of U is bounded by Cx to the minus 1 over Q minus 1. So this is Riccati. Okay. Now, if G is a complement of the ball, and in that case, I assume that U is, then in that case, I take a solution, positive solution, then you have estimate like Laplacian gradient of U in the normal grad of U is bounded from above by C P over Q minus P. Okay, so this is, in that case, it is agonal. So when Q is bigger than P, essentially either it can be, for singularity, it can be of Riccati type, or aconal type at infinity. So there is a, but of course it is exchange. Okay. And for proving this technique, this result, essentially for proving the first estimate, we use a Bernstein technique, and we obtain this type of first estimate with a Keller-Osserman type technique, which says the following. If I define omega theta to be the B1 minus theta minus B theta, okay, this is the domain, then I have a max estimate of the max of grad U is bounded by 1 over theta epsilon. Epsilon is a free parameter to the 1 over Q minus 1 plus 1 plus the max of U to the P over Q in a slightly larger domain, in the domain theta over 1 plus theta epsilon. So it is slightly increasing, but it is very important to see here that it is P over Q, and P over Q is less than 1. And how do we get this type of estimate? We use, we write Z is grad U to the square, and this is the Bernstein technique, and we obtain this type of estimate for Z minus delta Z plus M square over N Z square plus C1 grad Z square over Z, C1 is positive, plus C2 plus U to the 2P plus C3 U to the Q P plus P minus 1 over P plus 1. Okay, in the case of estimate, this coefficient here within C1 is positive, it's not a problem. I think this is something that we have proved with Marta Garcia Widobro and microscopes. Okay, so the key point you have to essentially, so it looks like an equation. You say, well, I'm going to use essentially a Keller-Osserman, and the classical Keller-Osserman you have to increase a little in order to have an estimate inside. You have to take care of this coefficient in a slightly bigger domain. That's the reason that we have this here. And of course, this is the coefficient which appears as in Keller-Osserman. Okay, so you see that when Q is less than after that, yes. After that, in the case when Q is less than P, we say the role of the aconal equation which plays fundamentally in the proof of the next result, and that we prove by doubling, by using again this theorem 3 and doubling lemma. And this is the following result. I assume that P is bigger than 1. M is positive, R0 is positive. When Q is between 2P over P plus 1 and P, then the solution here, in that case, the solution in the ball P, R0 minus 0, is bounded from above by Cx to the minus gamma, that means aconal, and the same with a gradient, but this is more standard. So this is in a slightly smaller ball. Now, on the contrary, when Q is less than 2P over P plus 1, and I take a positive solution in the complement of this ball, which goes to 0 at infinity, then we have again this type of estimate here. So this is type of estimate, but provided, of course, we have this. So this is a reversion of inequality, type of inequality of the assumption. Okay. Okay. Finally, I have just a counterpart of theorem A, which is it was this one. And what happens in the case where Q is bigger than, in particular, the case Q is bigger than 2P over P plus 1, okay? Then we have the following. You assume that P is less than N plus 2 and minus 2. Okay, this is critical in the technique because we use the doubling lemma, so it's critical to have this estimate always. And U is a positive solution in the complement of this ball, which goes to 0 at infinity. So we assume either Q is between 2P over P plus 1 and 2, and M is arbitrary, or Q is 2p over p plus 1, and M is small enough. So this is in some sense the framework of Quittner, Souplé, and Polacek, and this is the framework of that we did with Marta Garcia-Udoglo and François. Okay, then what you have a positive. There exists a positive constant, so that u of x is bounded by cx to the minus 2 over p minus 1, and grad u of x bounded by the derivative of this one, that means minus p plus 1 over p minus 1. Okay, this is more or less. It's a classical technique of blow up at infinity. Well, classical, it's not so classical actually, because the blow up was not at infinity up to now. But essentially, this technique that it reduces, since it is at infinity, it reduces this equation by the blow up. It reduces the equation to the Lane-Hamdan equation, okay, or the perturbation of the Lane-Hamdan equation, which is which is in that case when Q is 2p over p plus 1, and for that the smallness of M is important. Okay. Because when you study singularity, isolated singularity, it's important that Q is less than 2p over p plus 1, because in the blow technique you have to kill the coefficient of the gradient. When you go at infinity, since you have an expanding term, you have to also to kill the exponent of the gradient, so that you have reduced to the Lane-Hamdan equation. But of course, it reverses the range of Q. Okay, now if we want to go with all those estimates, can a little study called isolated singularity and removable singularity. So we have two approaches for that. There are two approaches of that. There was this equation. There is a capacitary estimate in the spirit of Barras and Pierre, and which is based upon variational techniques and geometric techniques that I introduced in a long time ago, in 1981, which made upon some geometric construction. Okay, so I want not only to eliminate a point, but I want to eliminate a set. So, of course, the geometric technique we assume that the set is a submanifold, while the capacitary technique assumes that the set is just a Borel set. And the first result is about in the geometry, with a geometric framework. I assume that P is positive. Q, okay, no, first result, I'm sorry, this is the first result is without geometry. It assumes that P is positive, Q is bigger, the max of 2 and P, and M is positive. You take now a sigma, which is a compact subset of omega, with C1 Q prime capacity 0. This is the classical capacity. Then you take any positive solution in omega minus sigma, then this solution remains locally bounded and can be extended as a weak solution in omega. Okay. And okay, the proof of this result involves many technicalities. I think it is close to a former result of Bresis and Nirenberg, which is valid in the case Q equal 2. Was the case Q equal 2. And it's to take, the idea was to take a test function. So actually you look at what happened, what is the equation satisfied by U to the 1 minus P. But after you have to make truncation to justify these things. So you multiply the equation by U to the minus P times eta K, which eta K is a function which defines in some sense the capacity. And G theta is a function of sine plus, it's just a reasonable approximation of sine plus. Okay, and then you compute. What do you get? You get that this in this form, which is a bit it's big, heavy. And this is the important term which contains most of the information here. And what you have at the end is less or equal to lambda n of t, which is a measure of the set where u is bigger or equal to t. So t is just a free parameter. And this term, you are going to control it by order. For that, you introduce this function, s of t is q over q minus p times t to the q minus p over p. And if q is less than q is bigger than p, and s of t is just the logarithm of t if q equal p. And now for s very large, you obtain this estimate that integral of the grad of s of u minus little s here is to the q is bounded by c times the measure of the set where s of u is bigger than x. Okay. This is I say that if q equal to it's a Bresis technique, but for q it's more complicated when for general q. Now, since the previous estimate here also works, since q is bigger than 2, it works if you replace q by q prime or q prime. And now you use Sobolev inequality, and what you get this type of estimate here. Okay. And you take now you define this function, phi of s is integral of omega of s of u minus little s to the plus dx, which is integral of s to infinity of, remember, the nu of t, which is a measure function. Okay. And you have this, it satisfies this inequality that you can integrate. And what you get at the end, that s of u minus s plus becomes 0 for s large. And you are done. Okay, now the second result, it's important that case that you need it's an extension of the method of Barras and Pierre himself and Bresis-Nirenberg, but it is strongly used strongly by a variational approach, a priori estimate or something, and integration by part. So now the other approach, which was something that I've developed in 81, was essentially to the following. You take omega is a bounded domain. You take sigma is a k-dimensional compact complete submanifold, where k is less equal to n minus 2, but can be 0. And you take 1 is less equal to p less to q. And you assume that q is bigger or equal to the codim of sigma divided by the codim of sigma minus 1. So if it is a point, it is n over n minus 1. Okay, if sigma is just a point. Then in that case, you can extend a solution in which is a positive solution in omega minus sigma, remains locally bounded and can be extended as a weak solution. And the idea is essentially to construct a tubular neighborhood around this capacity, about the state, sigma, I'm sorry. And okay, use again this type of estimate that we can get. Okay, because q is bigger than p, that means the max of the gradient in a sum. Okay, this is a kind of truncated tubular neighborhood here. So it is a kind of, you have the sigma, you take a little tube t, you take out the tube t, the tube of length theta, and you take a bigger tube here. Okay. And what you have this one, the same type of estimate as the previous one, okay? And with this, you obtain this type of estimate again. And now when you have this, you use called Weil's formula, which essentially can give you what is the volume of a tube. The volume of a tube is given by sum of the distance tau to the set to the manifold sigma is essentially given by this type of polynomial. And after that, you construct, after the technique became a bit standard, because you use again this type of function here, which are defining which are 0 close to the sigma and 1 a little further from sigma. And what you obtain that UP is in L1 and grad UQ is in L1, and after that everything is clear. Okay. So this is a different, totally different approach. You know, this for proving removable singularities when you have a problem which are not variational, like even for equation of fully nonlinear equation, you cannot use the technique of Barras and Pierre. You're obliged to use a technique of a geometric approach in the a priori estimates. Okay, I'm going to say a word, I think, on isolated singularity. If I want to study isolated singularity, so important fact is to study specific solution. And specific solution, okay, they exist only in the case Q equal to P of AP plus 1. So in that case, you have a separable solution, which are U of R and theta. Theta is a variable, a spherical variable, which satisfies this equation on the sphere. Okay, this equation on the sphere. And now for this equation on the sphere, when Q is 2P of AP plus 1, of course, you cannot have this term, and you can get either a dominant case at infinity is a Lane-Emden type, or Riccati type, or even a Conant case. So this is a full zoology of solution. And now, if we want to study, just to recall, okay, the Lane-Emden equation, the stationary solution of Lane-Emden equation, that means I call stationary equation, that means separable solution. Okay, I call stationary because of the use of technique of we use when you use equation in an infinite cylinder with a T variable, which is a Galism of R variable. Okay, so I have the associated equation is this one. This is called the Lane-Emden equation. Then the Riccati equation, so you kill now this term, and the aconal equation, then you kill the diffusion. So these are the three stationary equations which are naturally associated to the equation Ln PQ is 0, and which is, and if since we are studying asymptotics, in that case, we are going to kill one of the, if your Q is different from 2P over P plus 1, we are going to kill one of the terms, can be either the gradient or the terms due to the P. So in that case, we shall find either the Riccati type or the Aiken or the Lane-Emden type. Okay, I'm not going to describe too much this the set of positive solution because it's a bit standard. And I'm just going to tell you what are the asymptotics. Asymptotics is this result. Okay, I look at P is between n over n plus 2 and minus 2. Q is 2P over P plus 1, and U is a positive solution, is a puncture ball. Then either U is a classical solution, or we are the following. When Q is less than n over n minus 2, then essentially the behavior is like x, k times x to the 2 minus n. Okay, that means like the fundamental solution. And logarithm when dimension is 2. Okay, when n is larger or equal to 3, and p is n over n minus 2, so this is that case. There is a complicated, very complicated behavior, which was proved maybe 30 years ago by Aviles, and saying that the blow up of the equation minus Laplacian of U equal U to the n over n minus 2 is driven by this expression. That means x to the n minus 2, even multiplied by minus log of x to the n minus 2 over 2 U of x converge to this specific constant or 0, of course, but it can be also 0, of course. And now this is the result of Gidas and Sprack. That means that if n is larger or equal to 3, and it is a similar result, except that because here we kill the gradient. When there is no gradient, this is the Gidas and Sprack. When there's no gradient, this is Aviles, okay? And again, and this is that case again without the gradient. This is the previous result of Pierre Williams. Now we add the gradient, remember, so we have to kill the gradient at the end. But this is a good range for such. So when P is between n of n minus 2 and plus 2 n minus 2, u of x to the alpha u of x converge to this specific constant when x to 0. Can be also 0, of course. And the technique is this one. That means you use this transformation here. You write this equation. So this is u of r and theta times r to the minus alpha v of t and theta, with t is a logarithm of r, it's called m then variable. And you have an equation in infinite cylinder. And you see that this, in that case, because you have the sign of sigma, because the sign of sigma, in that case, that we know that q is less than 2p over q plus 1. So when t goes to, r goes to 0, so t goes to minus infinity. So in that case, this term is cancelled at infinity. So essentially, after that, it is a standard technique of dynamical system in infinite-dimensional dynamical system, but without difficulty. We have not completely. We do not have really a first integral, a Lyapunov function, but we have a Lyapunov function perturbed by something that we dominate. This is the energy function. The derivative of the energy function is a good one. So this one, when m equals 0, this is a classical form. And now it is perturbed by this here, but this is bounded. So after that, the proof is a bit standard, and I think I'm going to stop. Okay. Yeah.
Any question, comment?
So suppose you eliminate the term due to the Q,
Yes.
how many of these things disappear?
How many of
Which
them?
is left?
When you just have in that case, it's minus Laplacian of u plus m gradient to the q.
Yeah,
Okay, but this is classical. This is something that I did with, I think, with Thai, Wienberg Thai.
what is the part that disappears?
The part. So I shifted. I've not seen. You have not seen. Essentially, you have that x to the when you are prior estimates. It says that essentially. Okay, you may have isolated singularities. I think the critical value is n over n minus 1. Okay, this is for the removability. Okay, this is the same as we have seen before. And now when q is less than n over n minus 1, so you look at x. So the critical exponent is beta, because it corresponds to the Riccati equation, and that you have x to the beta times u of x, which goes. Either it goes to 0, if it is just an isolated singularities, or it goes to a specific solution that I have not. I have given that very briefly, which is a solution called the separable correspond to separable solution of the Riccati equation, which is some equation on the sphere, which has a unique solution to this. The most difficult case is the case of the remaining when you kill the diffusion. When you kill the diffusion, this is a bit very complicated.
Any other question, comment?
What will be if the absorption term and the right-hand side will have the same structure, the gradient of the power function? Or
I think you put everything on the same. What is the equation? Minus Laplacian of u?
for Laplacian of u, and you have the absorption term and the right-hand side, this function
on the same sign,
Yes, not the same sign.
at the same time, UP
with the
plus
same
UQ.
sign.
Okay, UP plus UQ, how many results from
UP
that?
minus gradient U to the Q, minus delta U plus UP minus gradient U to the
Okay.
Q. We have done it before.
Yeah, this is
It's
fine.
much simpler
Yes.
because we can use a super and
Yeah,
sub
yeah,
solution.
very simple.
And here we cannot use at all. We are obliged to use Bernstein techniques and just
No, but maybe
quite
also
more
she wanted me to know if it is minus operation U, is UP plus UQ, no? Or minus
No,
UQ? It's very complicated.
the-
You can play a lot with that.
the-
But when
We-
when the dominant term is really, when the dominant term, that means it's not Lane-Emden, in that case it's called it Emden-Fowler equation, minus the Laplacian of U plus UP equal M grad UQ, then it is much easier because we have comparison technique and we have immediately the Keller-Wasserman method, the development of Keller-Wasserman method linked to the Bernstein techniques. It's no problem.
You can put, you can have 4 types of equations
Yeah.
according, but the simplest is minus delta U plus U to the Q to the P plus gradient U to the Q equals
Yes.
0.
It is done by
Only
the
absorption. And the most difficult is this one.
Okay, Professor Giga has a question.
Yeah.
Please,
Okay.
Professor Giga.
Thank you for your very nice talk. I have one maybe very fundamental question. If you have the boundary, is it possible to study the asymptotic behavior of singularity near the boundary, or removability near the singularity near at the boundary?
Okay, now we have a previous result about boundary singularities of boundary singularities for this type of equation. But it is simpler actually. For many things, it is for me it's a bit simpler than the case of at least for measure. For example, if we want to study the problem with boundary measure, it is simpler to construct than the one problem inside. And for a simple reason, because first you want to, if you have a boundary measure, you can solve the equation minus Laplacian of U equal UP inside and U equal to some measure on the boundary. So it is natural super solution, and minus Laplacian of U plus grad UQ is 0, and U is equal to the same measure mu. It's a natural sub-solution. So in the domain itself, you have a solution of this equation which is between the super and the sub-solution. And at the boundary, we have the boundary trace because the equation, the solution is taken in kind of say as a sandwich between the super and the sub-solution, which have the same behavior. So you can construct a solution like this.
I see, I understand. So how about you at the beginning of the talk, you give us a couple of estimates, for example, gradient estimate. Such estimate also easy to obtain if the domain has a boundary with Dirichlet or Neumann boundary condition.
It's not a boundary, we do not have much estimate like that. I think we emphasize on the question we have a zoo of isolated isolated singularities, because you can extend this type of problem with at least for the Riccati type or for the Lane-Emden type. You can construct a singular solution. For the econal, it is too rigid, so you cannot get it. And you have also in the case Q equal 2p over p plus 1, you have a boundary problem. At least we can study a solution, but the difficulty is that the solutions are defined, for example, in a half ball, and the half a sphere. Your problem, you replace the sphere. When you look at separable solution at a singular point on the boundary, you say, and you want the solution, for example, U to be 0 outside the singular point. Then when you make the blow up, you have a solution in Sn minus 1 plus times R. So an Sn minus 1 plus, it is half sphere with solutions which are 0 on the equator. So this is not, you cannot say, well, we're going to have constant solution. No, it doesn't play like that. You can, in some cases, you can construct solution specific solution, but they have to vanish on the boundaries. The solution of this equation on the upper hemisphere, vanishing on the boundary, and it's a bit more complicated. We have example, of course, no uniqueness can be hoped. We cannot get this.
Thank you very
But it was
much.
the case, even the case of when we look at the boundary isolated singularities of Lane-Hamdan equation. This is a former paper that we did with Augusto Pons and Marie-Françoise. It was 20 years, 15 years ago. We have the same
I see.
debate.
Thank you very much. Thank you very much.
Of course, you have many questions to discuss, but please use a coffee break. So then let's coffee break now. No. Okay, let's start speaker again. Please prepare. Okay. Next speaker is Professor Shinya Okabe from Tokyo University, and his title is Recent Advances in Sovereign Gradient for Curves.
Thank you, Chairman. First of all, I'd like to thank all of the organizers for giving me an opportunity to give a talk in such a wonderful conference. It's my great pleasure to give a talk here. Okay, let's start to talk about recent advances in sovereign gradient plot for curves. In my talk, there is no relation between the nonlinear diffusion, but I hope you can enjoy my talk. So the first part of my talk, we consider the H2 gradient flow for elastic energy defined on curves. First, I would like to introduce the elastic energy. So let gamma be a closed space curve, and for curves we define the following energy functional. Here, lambda be a given non-zero constant, and script L denotes the length of the curve, and capital E is given by the square integral of kappa along the curve gamma. Here, kappa denotes the curvature of the curve, and the parameter S denotes the arc length parameter of curve gamma. And here, the energy functional capital E is holds the elastic energy, or the Euler-Bernoulli bending energy. And the critical point of the functional capital E under the length constraint is called elastica. And for example, for the case n is equal to 2, so planar closed curves, if gamma is an elastica, then gamma is a circle or figure 8, or a multiply covered circle or multiply covered figure 8. On the other hand, if the dimension n is bigger than or equal to 3, then there exists countably infinite families of non-planar closed elastic. The purpose of the first part in my talk is to give new sovereign gradient trajectories to elastics. In 1985, Langer and Singer considered a gradient flow for the elastic energy, using the fact that the elastic energy can be regarded as the Dirichlet energy of tangent vector. They derived H1 gradient flow for the elastic energy, and which is written by second of the parallel equation with non-local term. And the work by Lang and Singer was extended into the L2 gradient flow, which is the fourth order parabolic equation. And the equation has been studied well by many researchers. And then the purpose of the first part of my talk is to give the H2 gradient flow for the modified elastic energy. Okay, from now on, we derive the H2 gradient flow for the modified elastic energy. From now on, we set I2 with the set of the H2 closed curves with such a regular condition. And for some curve gamma in the class I2, we define the following H2 inner product. But here, please remark that the variable S is the occurrence parameter of gamma. So it's not standard H2 inner product. How to say that? Non-flat H2 inner product. And we define the H2 norm as usual. And in order to define the H2 ds gradient flow, it's sufficient to define the H2 ds gradient of the functional at gamma. And we define the gradient as follows. If we can write the first variation of the functional at gamma in terms of the H2 ds inner product, then this is the H2 ds gradient of the functional. This is the definition. Okay, from now on, we derive the precise form of the H2 ds gradient of the functional. To do so, we calculate the first variation of the functional at gamma. And by a simple calculation, we can derive the so here we write the L2 inner product. So this is the L2 ds gradient of the functional, and this is the fourth order. So if we consider the L2 gradient flow for the functional, then it will be a fourth order parabolic equation. Here, first we write the H2 ds inner product. So by integrating by parts, we derive the H2 ds inner product in terms of the L2 inner product. Then the required H2 ds gradient is a solution of the fourth order equation. Here we let the capital Z be the green function corresponding to the equation. Then we can derive the required H2 ds gradient of the functional by the convolution of the green function with the inhomogeneous term, like this one. And now we have already derived the precise form of the L2 gradient. So we substitute the precise form here and integrate by parts. We can derive the precise form of the H2 ds gradient of the function. Then we can consider the H2 ds gradient flow for the function. Here, please remark that the H2 ds gradient flow can be regarded as an ODE in the H2 space. So from now on, we consider the Cauchy problem on the H2 ds gradient flow. The main result of the first part of my talk is the following. This is the joint work with Philip Schrader in Murdoch University. Let gamma 0 be an initial curve in the class I2. Then the Cauchy problem P has a unique global incident solution in the class I2. And moreover, the global incident solution converges to elastica as time goes to infinity in the sense H2 metric. And for gradient flows for elastic energy, it is standard assumption that the problem has a unique global intent solution, and the solution converges to an elastica along a sequence of time, namely global intent solution sub-converges to an elastica. So the point is how to extend the sub-convergence to the full limit convergence. For L2 or H1 gradient flow, it was proved that we can take a full limit under the up to the some deparameterization or translation. But in our result, we do not need to take any translation or reparameterization to take the full limit. This is good point of my theory. Okay, in the rest of my first part of my talk, I'd like to mention the outline proof of theorem 1. So, as I said, our H2 gradient flow can be regarded as an ODE in the space H2. So, verifying the Lipschitz continuity of the H2 gradient of the functional with respect to gamma, and employing the generalized Picard-Lindell theorem, then we can easily prove the existence of local intent solution. Okay, we come to the existence of a global intent solution. To do this end, we use the following metric on curves. Let alpha and beta are curves, planar plot curves. Then we define the distance between alpha and beta as follows. Infimum of the integral of p prime. Here, please remark that the parameter SP denotes the occurrence parameter of curve P. Here, the set capital P is the set of C1 paths connecting alpha and beta. And the metric very fits our settings, namely the metric space I2 with the distance is a complete metric space. Then the completeness gives us the key lemma to prove the global intent, the existence of global intent solution. So this is the key lemma. So the assertion is if we obtain the integrability, then we can take a limit in the sense of I2, in the H2, in the sense of H2. So the proof is really simple, easy. So take some sequence, any sequence such that converges to B and J goes to infinity. And we consider the family of curves gamma of Tj. Then, by the definition of the distance, so please remark that gamma is a path connecting gamma of Tj and gamma of Tk. So by the definition of the distance, the inequality clearly holds. Here we use the assumption, then we can easily see that the right-hand side converts to 0 as J and K goes to infinity. This means that the family of curves gamma of Tj is a Cauchy sequence in the metric space. Then the completeness implies lemma 1. Thanks to the lemma 1, we can show the existence of global intent solution by contradiction argument. So assume that the maximal existence time is finite. Here we consider the difference of the energy between our solution to the initial curve. And it's clear that this difference is written in the integral of the derivative of the energy. And here is the definition of the H2 gradient. And now we consider the H2 gradient flow for the functional. So the third equality holds. Here we consider this integral, and by Helder inequality, the right left hand side bounded by the square root of P max times the squared integral from 0 to t max. And by the equality, we can estimate the squared integral by the difference of energy, and we negligible of one. Then we obtain such a uniform bound. Then gamma satisfies the assumption of lemma 1. So lemma 1 implies the existence of the limit as t goes to t max. Then we can extend the solution a little bit by short time existence theory. So this is a contradiction. So we turn to the full limit convergence. As you see, in order to show the full limit convergence, it's sufficient to prove the L1 integrability. Indeed, if we obtain the L1 integrability, then lemma 1 implies that we can take a limit on gamma as t goes to infinity in the sense H2. So the point is how to, on the other hand, as you see, squared integrability is easily solved from the energy structure. So the point is how to extend the squared integrability into the L1 integrability. The one of useful tool to obtain the L1 integrability is the Weierstrass-Simon gradient inequality. And the Weierstrass-Simon gradient inequality for our H2 gradient flow is also our contribution. So this is also our main theorem. And so here, let gamma infinity be a critical point of our functional. Then there exists some triplet of the positive constant such that for any curve in the class I2, if gamma is close to the critical point in the sense of sigma, then H2 gradient of the function at gamma is bounded from below by the difference of the energy. And the theta, constant theta is the power of the difference. And roughly speaking, theorem 2 implies plane 1. Indeed, here we let the function character h by the difference of the energy between the solution and the critical point in the equilibrium to the power minus 1 minus theta. And here, please recall that the equality holds because we can easily obtain the equality by using a definition of the H2 gradient and H2 gradient flow. Here we consider the minus the derivative of H is so to the power minus 1 minus theta times time derivative of energy. Here we use the equalities, and the inequality form from the Weierstrass-Simon gradient inequalities. Then we obtain the lower estimate of the derivative of capital H, and capital H is non-increasing, so integrating the both sides, then we obtain the L1 integrability, required L1 integrability. Then we can prove the full limit convergence along the standard argument. Okay. So finally, we close the first part of my talk with the alternative proof of theorem 2, Weierstrass-Simon gradient inequality. We employed a strategy by Pihan Maridakis in 2020. The first, we will check that our functional is analytic. And next, the second condition is the second variation of our functional at a critical point is a Fredholm operator. Here, operator F is a Fredholm if and only if the operator is linear and continuous, and the dimension of kernel and the codimension of the range are finite. And the index is the difference of the dimension and the codimension. And on the first condition, we can check the analyticity of our function. It's easy. But on the second condition, there is a difficulty because if we find some curve belong to the kernel of the second variation, then its any Lie parameterization also belongs to the kernel. This means that the dimension of the kernel of the second variation is not prime. So this means that the second variation of our functional is not predictable. So how to overcome the difficulties? Here we define the following function, the difference of local length and total length, and define the omega by the inverse image of phi. So if gamma belongs to the space omega, then this means that its local length is identically equal to total length. So this means that we consider only some curves with special parameterization. It's so-called constant parameterization. So we fix special parameters. Then first we check that the omega is an analytic submanifold. And next we prove the second variation of the restricted functional is Fredholm operator. Yeah, we can do it because we have already fixed some special parameters. So then we can obtain the Wetley time on gradient inequality for the restricted energy functions. And finally, by estimate, we extend the restricted version to the required one. Then we obtain the cell 2. Okay, so yeah. Okay, we come to the second part of my talk. In the second part, we consider some gradient flow, H1 gradient flow for some kind of Dirichlet functional defined on curves, and its application to the isoperimetric inequalities. Okay, from now on, we consider the following energy functional. Here, from now on, we denote by S1 R over 2 pi Z for short. Yeah, pretty remarkable. And here, Q is the Dirichlet energy defined on curves. And A, capital A, denotes the signed enclosed area by gamma. Okay. And here, R denotes the counterclockwise rotation through the angle pi half. Okay. And we consider the H1 dx gradient flow for the functional capital E. Here, please remark that this H1 dx is a standard H1 space. X is independent of gamma. In the first part of my talk, we consider H2 ds is not flat, non-standard sovereign space, but this H1 dx is a standard sovereign space. So along the same line as in the first part, in order to consider the H1 gradient flow, we define that H1 dx gradient of the functional is the same. It's the same speed. Okay. So to derive the precise form of the H1 gradient, first we calculate the L2 gradient of the functional. It's a simple calculation. Second order, the later. Then integrated by parts, we write the right-hand side H1 in the product in terms of the L2 inner product. Then the required H1 gradient is a solution of the equation, second order equation, and the inhomogeneous term is L2 gradient. So here we use the same notation, but here Z is the green function of the layer on S1, written in this form. And please remark that in this case, Z is independent of gamma. It's only the function. Then we can derive the H1 gradient of the functional as the convolution of the green function with the non-homogeneous term. Integrated by parts, we can derive the precise form of the H1 gradient, and we can consider the H1 gradient flow for the functional. Here, please remark that the H1 gradient flow can be regarded as also ODE in the space H1. So, first main result of my second part is probability of the H1 gradient flow. Okay. So if we hold any initial curve in the H1 plus, here H1 plus denotes the H1 curve with positive enclosed area. Then our problem has unique global integral solution in the class H1 plus, and the solution converges to multiply curved circle as time goes to infinity in the sense H1. Then this is a standard H1 Fourier space. And here, please remark that the equilibria of our problem consists of only multiply covered circle. So here I'd like to mention the outline of proof of theorem 3 quickly, because the spirit of proof is similar to the first part of my talk. Indeed, as I said, H1 gradient flow can be regarded as an ODE in the H1 space. So first, to verifying the implicit estimate of the first H1 gradient with respect to gamma, and employing the generalized Picard-Winders theorem, then we obtain the existence of global interim solution. And on the existence of global interim solution, the key lemma is the following. So we can obtain the estimate by a simple calculation. So I will skip the detail, but if we obtain these key estimate, then we can extend the local interim solution for more easy, very easy, because the maximal existence time depends on these factors, so we can easily extend and extend. Okay. And on the convergence, so as I said, in this case, we consider the standard Fourier space. It's a flat, so there's no extra difficulty, such as H2DS gradient flows. So we employed a strategy given by Pihan in 2020 by using like most property something, then we can prove the Wesley-Simon gradient inequality. Once we obtain the gradient inequality, then we can show the Coulombic convergence by a standard argument. Yeah. So in the rest of my talk, I will show you an application of H1 gradient flow for to the isoperimetric inequality. Okay. So as you know, the isoperimetric ratio of curve is given by squared length over 4 pi times enclosed area. And as you know, the classical isoperimetric inequality is the isoperimetric ratio is bigger than or equal to 1, and the equality holds if and only if gamma is a circle. And in this talk, we are interested in the following generalized isoperimetric inequalities. More precisely, pick some number, integer n, bigger than 1. And the question is, what is the largest class xn of immersed? Immersed means we allow the self-intersection curves. Immersed closed curves such that the generalized isoperimetric inequality here, lower bound is not 1, it's n, given number n, for all curves in the class xn. And here, first please remark that the equality attained by the n times curved circle. Okay. And next, so we need some extra condition on xn to show the generalized isoperimetric inequalities. Because if we consider the circle, generally the number n is defined by the rotation number of curve because the integral average of curvature. Okay, so if we consider the curve circle with a positive small n-1 loops, then its rotation number is equal to n. But if we let the n-1 loops smaller and smaller, then we can easily check that the isoperimetric ratio of such a curve is very close to 1. So such curve does not satisfy the generalized isoperimetric inequality. So we need some extra condition on Xn. Indeed, there are several results on the generalized isoperimetric inequality under the rotational symmetric condition. Here the definition, let n be natural number, then growth curve gamma is m's rotational symmetry. If and only if we can find some number which is less than or equal to m, such that gamma satisfies the relation. Roughly speaking, if gamma is m's rotational symmetry, then gamma is constructed by one piece by rotating. Okay. So for such a under the m's rotational symmetric condition, first in 1987, Stein gauge proved the generalized isoperimetric inequality under the highly symmetric condition with locally convexity. Locally convexity means that the curvature of the curve is a positive function. The highly symmetric condition is extended by several papers, Cho in 2003, and Satnam in 2011, and Wang Li Kao in 2017. However, they also impose the locally convexity assumption. And in our previous work, it's the joint work with Professor Tatsuya Miura, is the last speaker of this conference today. Okay. We eliminate the locally convexity assumption. Here, please remark that in these works, the number n is regarded as a rotation number. It's an integral average of the curvature. So this means that in this result, the curve gamma should be W21 at least. But however, probably the variation argument in our previous work can work well for more weak settings. But today I will show you another proof and generalize as perimetric inequality for more weak settings by using a H1 gradient flow. Indeed, we obtain the following result. Let gamma be a H1 curve. Then the classical isoperimetric inequality force and the equality was if and only if gamma is a single circle. It's a right circle. And moreover, for the generalized isoperimetric inequality, we add the m's rotational symmetric condition and the relation between n and m. Then we obtain the generalized one, and the minimizer is n times covered. Yeah, we close my talk with the trial proof of 7-fold. So we gave a dynamical approach to the generalized isoperimetric inequality. Okay, first we show a classical isoperimetric inequality. Here is the essential role of H1 gradient flow. So first we consider initial curve. So we take an arbitral curve in the class H1 plus with some special parameterization. It's a kind of constant parameterization. We can take a reparameterize because we consider H1 curve, so we can take reparameterization. Okay. So if we take such a curve with special parameterization, then the dirichlet energy is equal to length squared over 4 pi. Okay. Then here we take a H1 gradient flow starting from the initial curve gamma 0. Thanks to the quality, the isoperimetric ratio is equal to our energy function E. And now we consider the H1 gradient flow, so we can take the full limit convergence to an equilibrium. And here is followed from Helder inequality. Then we obtain the estimate on the isoperimetric ratio on the initial curve and some equilibrium of our problem. And as I said, the equilibrium consists of only multiply curved circle. So the capital gamma is a multiply curved circle. Okay? For example, it's L times curved circle. And here L is a natural number. So we clearly obtain the classical isoperimetric inequality. Okay. So we extend the argument to the generalized isoperimetric inequality. This is the final slide of my talk. So here is the same argument as in the classical isoperimetric inequality. So take an initial curve, fix some any curve in H1 plus with special parameterization, and now we also impose the rotationally symmetric condition on initial curve. And we take a H1 gradient flow, then we obtain the estimate on the isoperimetric ratio. The same argument as in the classical isoperimetric inequality. And moreover, the gamma is an equilibrium, so gamma is a multiply curved circle. Okay. And now we use M's rotational symmetric condition. So our problem is invariant under the rotation and shift. So we can check that the equilibrium is also satisfied M's rotational symmetric condition. So for example, this equality is M's rotation symmetric condition on the circle. It's with the center is origin, right? The vector rotate of the vector is given by the end point of the first piece, right? And the equality clearly implies the relation between L, N, and M. And here, L is the number of the, so now gamma is L times covered circle, so L is bigger than or equal to 1. And we assume the relation between N and M. Then, combining the condition with the relation, then we easily see that the K is a positive integer. This means that L is bigger than or equal to N. Then this implies generalized isoperimetric inequality. Okay, I think I should here. Thank you for your kind attention.
Well, any question, comments? Okay, I have two questions about the first part of the talk.
Yeah.
In the first part of your talk, energy has parameter lambda.
Yeah.
What is the role of parameter lambda? If you change the lambda, then structure of stationary solution should be changed.
Yeah, roughly speaking, lambda is so radius of the, for example, if the equilibrium is a circle, then lambda is related to the radius of the circle. And if we take lambda is equal to 0, then the compactness of the flow will be lost because it's a bigger and bigger circle. Yeah, it's like a penalized term on length.
For some lambda stationary,
As I said, for the planar case, planar closed curves, then the critical point is a circle or multiple covered circle or figure 8 or multiple covered figure 8. So no unit.
the other question is, you have in the H2 gradient flow, your solution converges to a stationary solution without any subsequence, all full depth.
Yeah.
So, but the other gradient flow, you have some troubles.
Yes.
You have to take a subsequence.
Yeah.
Yes.
Yes.
But you get a nice limit in the H gradient flow. So can you get can you improve the other gradient flow by using your result?
It depends on the Wesley-Simon gradient inequality. For L2 or H1 gradient flow, probably I think we cannot prove the Wesley-Simon gradient inequality without additional translation or rotation or reparameterization, because this is the point, is how to show the finiteness of the image of the kernel. Yeah, I think for in this case, we can use the completeness of the metric space, but for other case, we cannot use, there's no such a completeness. So generally, we can not show that the second variation of the functional is a further form of operator without any translation or rotation or reparameterization something.
Okay.
Yeah.
Any other question, comment?
Yes, can you take into account some, let's say, generalized problem where in your RN space you have a force which penalizes some direction or favors some other ones, so that you change your critical points?
For example, you add another kind of constraint, fixed area, something like
you add I don't know, some stream which brings you to the left. What happens?
I'm sure about that. In my I'd like to say that if we take some suitable metric for the energy functional, then we can get some good ones. For example, if for the length functional, if we take a L2 gradient flow, then it's a curve shortening flow. It's a second of the parabolic equation. There are so many interesting research, but generally such a flow has a singularity, finite time singularities. On the other hand, if we consider the H1 gradient flow for the length, then there is no such a finite time singularities. So I'm not sure for only a question about that. If we choose some suitable metric corresponding to the energy functional, then we can get some good ones on that. Sure. Sorry for your
That's it. Thank you very much.
Any other question, comment? Okay, let's start speak again. We have coffee break and we do stuff.
Yes, the next session.
You have a
Just a quick announcement. First, don't be scared if you see a lot of people coming out from the main room there, because there is another event of science of alimentation or whatever in the institute. The secretaries asked me to tell you this. Second thing, if some of you still haven't signed, now it's now or you don't get a reimbursement. And also please fill the thing of the lunch as soon as possible. I think that this part we haven't seen it. So before the coffee break, just put your thing there and give it to me, okay? And sorry for for this short announcement.
And the next session will start noon.
Yes. 30. Yeah.
ありましたね。